So for the last lecture video for this day, we're going to talk about hydrated metal ions as acids. Now, in a previous video, when I was talking about the chelate effect and food preservatives, I made this statement about how sometimes metals can not only induce oxidation reduction reactions, which would spoil your food, but they can also act as acids. And we're going to see that now. And specifically, when we have a hydrated metal, it can actually induce the creation of protons in solution. And so what we mean by a hydrated metal is one that is completely coordinated with water. So here we have the Hexa Aqua iron 3 complex ion. And as it turns out, this is another one of these examples in chemistry where we haven't totally been truthful with you. Generally, when we put most metals in solution, they become this. And not all metals do this, but mostly the what I'll call highly valent. So highly valent means it has a large oxidation state. In this case, iron being +3, that's a fairly large oxidation state. Or there are certain metals that are hygroscopic. And so what that means is they really like to interact with water. So we could also say that they're hydrophilic. So they love interacting with water. Okay. So now when this happens, this gets rather complicated. So let's take a deep dive here. So we can see our iron 3, and it's surrounded by 6 water molecules. So now in the vicinity of a neighboring water molecule, we actually get some chemistry going on here, okay? So because of this large valency, so the high positive charge, you can see what this cartoon is showing you. It's sucking electron density out of that oxygen, so it's pulling it away because it has a large charge. And what that does is it weakens this bond. So bond weakened. And you might be asking, well, why does it only do this on one and not the other? Because it's a very subtle effect, okay? So it's very subtle. So it only does this very weakly. So in other words, these acids are weak acids, very weak acids. But all the same, this large valency can suck electron density away from this bond. It weakens this bond. And now this water is a fantastic base, so it can accept a proton now from this water, okay? It has become a fantastic base because of the weakening of this bond. And now what happens is that gets deprotonated and it makes H3O+, okay? So if you also recall in your early days, your intro to qual assignment, we had another nomenclature for this, which is omitting the water. And we often do that to avoid complications. So another way I could write this reaction would be to not indicate the water. So I'm just putting iron 3 aqueous. And if we were really good at chemistry, and we'd have to be like really, really good at chemistry, we would recognize, oh yeah, iron is typically a hydrated metal. So I'm not going to show the hydration, but we would just recognize that it is hydrated. And so now when iron 3 reacts with one water, we've omitted all of those waters. So now we would just write this as FeOH2+, okay, because hydroxide is 1-. The Fe was 3+, so it reduces one of those charges. And then now what we're left with is a free proton. So these two reactions would both be the same. Okay, just one is like an abbreviated version of that. We could also write a Ka expression based off of either of these reactions because they're both the same. I'll write it as from the bottom reaction because it's a little bit simpler. So that Ka is going to be H plus times FeOH 2 plus all divided by Fe3 plus. And now our same equilibrium applies. We can make calculations of this based on the Rice table. We can also make pH calculations, right, if we knew what the H plus concentration was. And of course, that means we have to know the Ka for these hydrated metals. And here's a table of them right here. And if we look at this, what is the relationship between metal ion and acid strength? If we stare at this for a minute here, okay, if we look at all of the ones with small Kas, so remember small Ka, weak acid, large Ka, strong acid. So let's write that. I mean, these are all weak, but these are stronger and these are weaker. Sorry, my handwriting's a little sloppy. So now you notice as the valency of the ion increases, so these are all 2 plus, and within the series of 2 plus, there's obviously like a pretty big trend right here. And if we looked at our periodic table, let me, I need to move this out of the way. No, get out of here. Okay, let's see. You're gone. Okay. So now if we look at our periodic table, so for example, if I was comparing, let's start at the bottom there and see if we can work out a trend. Here's nickel, and here's cobalt, and here's zinc, and here's lead. Where'd lead go? I can't see very well on the table. There's lead, and then there's copper. So you can see that's all over the place. So it's really hard to kind of work out a trend amongst those ions. But what's important to note here is when we jump up to the aluminum 3 plus, the chromium 3 plus, the iron 3 plus, all of those 3 plus states, those Ka values increase pretty significantly, okay? So that's really the only trend I want you to recognize. The larger the charge of the metal, the better of an acid it's going to be, okay? And we'll do some sample calculations of this in the live lecture meeting.